So just a kind reminder, without a note taker, which simply takes the questions and the summary of the answer, we cannot start the meeting. So 1 or 2 volunteer would be perfect. Thank you.
Thank you, Marcus. You have been helping it in many working groups, so thanks for doing it. Do you need a backup? Like
That would be nice.
that would be nice. So somebody can back up, Wes. Thanks, Wes. Good. So it's 5. Let's start the meeting. Hello, welcome. This is a TIPTOP working group meeting, IETF 123, 123. And here I am, Jahidujaman Sharkar, and my co-chair on the remote, Padma. And we welcome you all here. And if you're not intended to be in TIPTOP meeting or in the space, this is perhaps the wrong room for you. So, but then with that, hello, Padma. I hand over to you for the, you can greet and start.
So I'm just taking control of the light. Okay. All right. So welcome everyone, as just Zayed had said. Please note, well, I think by this time everybody knows this, but I will give 30 seconds for you to go through this. It is a reminder that IETF policies are in effect and that you agree for IETF processes and policies, that you're aware of the contributions covered by patents and so on are now owned and controlled by you or by your sponsor, where you must disclose that fact. I will let you read the rest. Note really well. We want to maintain a technical environment for discussions with respect and must not engage in harassment. And if you believe you're harassed, please take this to ombudsman person. All right, here's the tips. The meeting is recorded. Please raise your hand to join the queue. All right, here are the resources. I'm going to fly through this. So this page is what are the working groups documents that we have and documents to be working group documents. So very happy to say that we've got our first working group document, which is the TIPTOP use case that was adopted. Today on the agenda, we'll have the TIPTOP use case, the IP architecture, also the DNS. We will also have another one, which is email. And then we have a number of non-working groups documents, like I said, which are going to be here, the architecture and the other works. So we'll have a couple of other works that's going to get presented today. I just realized that maybe this is not the latest version, but let's skip that. So anyway, let's get started. The agenda, the updated agenda is on the uploaded. So let's start with the use case requirements. Next to you, Marshall.
Marshall, you're up. Can you start? And you also have the control for the slide.
We already had a. Can you hear me now?
Yes.
Yes, no?
Yes, we can hear you.
Can you hear me now?
We can hear you. Yes, we have been hearing you. We can hear you. You can perhaps, yeah, you can write a chat.
I'm not actually hearing you.
Ah, okay.
Can you hear me now?
Can you hear us?
Yes, I can hear you. Sorry. Yes, I can hear you
hear
now.
me.
Great. Yes.
Can you hear you at the
All
front of the
right.
room?
Sorry. Let's proceed.
Sorry?
So I'm in the audience. Can he hear the chair? Can he hear you?
I can hear the chair. I heard him just now.
Marshall, can you hear me as chairs?
Yes, I can hear the audience and the chair. So
Right.
everything
Okay.
is good.
Now it's all done.
Okay. So I'm glad to say that we now have a working group draft. So this was a private draft. The version 1 was published on March 2nd, and I don't believe that the version 2 was discussed much in Bangkok because of the timing of it. I think it came out during the meeting. And so here I'm going to talk about changes from version 1. And so to give a little bit of overview too. There's, of course, an architecture draft, which I believe will be talked about in a few minutes. And there's the working group charter calls for that to be adopted by November, I would guess in time for the next IETF meeting. And there's also, of course, there's going to be some possibly migration between this document and that document. And there might be also some passing back and forth with the new IETF space research group. So let's go forward. So, I mean, the topics of the draft, the topics of the draft are here. I don't think we need to go into this very much. If people haven't read it, they should read it, of course. What we're trying to do here is you see coming down the pike very soon for the moon, a sort of new regime where there will be internet on the moon, between the Earth and the moon, and we need to do, and not just when I say the moon, not just the surface of the moon necessarily, but lunar orbit. Various kinds of lunar orbits will have different characteristics, and then the sort of mixed orbits like the Lagrange points, all of which we've been covered in these use cases. So, for example, lunar assets. Now, unfortunately, I was not able to share a really good image of the planned orbits for this, but what you see, the picture here is that this is from Intuitive Machines. This is a sort of their generic model for their orbits, which are not actually the orbits they're going to use for their lunar relay. This has actually been this 5-satellite lunar relay. Some of them share orbits, and basically what they plan to do is to do elliptical orbits so that it's almost like a Molniya orbit where you have the satellites hanging high overhead, desirable places on the moon like the South Pole for long periods of time. So they have long, more or less continuous relay capabilities, including on the far side. Generally, one of the interesting things about the moon is it's rotationally locked, of course, and so there is a far side. And you almost always find that communications to somewhere on the far side is different than communications to somewhere, say, on the near side of the surface, or something in lunar orbit or at a Lagrange point or whatever, because you can't see it from Earth. You have to have a relay, or you have to have a store and forward. For Mars, things are much less certain. I think it's fair to say. There is actually a MarsNet. Chad Edwards at JPL was the lead of the effort to do that. It was about 20 years ago, I believe. It's at UHF. It is rather old technology now. And as far as I know right now, it still is only concerned with bits. In other words, it doesn't know files or anything. Everything is just pushed through this pipe. But it's used routinely to go from the rovers on the surface to orbiters to the Earth. And it works. And there's been discussion about updating that for years. So far as I know, there is not much actually done on that in the sense of building hardware. But if we're going to go to Mars, we're going to need an upgrade of that. So in the requirements area, we have store and forward. We have a little bit on time. We have signaling, bandwidth, transport, addressing and routing, recovery on reboot, which is a new one, and security considerations. There was a security considerations before, but it just said TBD, so it's entirely new as well. So let's go a little bit finer draft here. Oops, finer grained. the introduction and limitations was substantially worse. I think it was substantially improved. And then a lot of that was based on comments on the mailing list. Also based on comments on the mailing list, we added a lot of references to the CCSDS, which sets a standard here, at least sort of from the space agency side. Also a mention of LunaNet and a reference to LunaNet. The text on slow-moving mobile networks was improved. The spacecraft on board was substantially rewritten. What that means, by the way, is a lot of spacecraft have on them a network, or maybe multiple networks. Not just Ethernet either. A lot of them have actually they're running internet on, or some sort of internet on the spacecraft, just to communicate between one piece and another. So, and actually nowadays with swarm spacecraft and multiple spacecraft, they're also using things like Wi-Fi to communicate between a piece here and a piece that, say, might be on the ground near the lander for a lander or whatever. All of this is being done right now. It's actually pretty complicated in some cases. It's kind of interesting what they're doing, and tend to be under NDA for a lot of this stuff, so can't talk about it in detail. But we do have a section on that now. Sections 4.5 and 4.7 were filled in. They were basically just stubs before, and the security section was entirely filled in. And so I would recommend that people read the security section. There's been some discussion of security in TIPTOP. Sorry. So we obviously need to continue this. I think the security section, having been an IETF chair in the past, I would say that probably does not yet have group consensus. I think we should work on achieving that. But I think, having been an IETF chair and having seen numerous drafts go through, this draft has received remarkably little dissension. I think it's in pretty good shape. I think the group seems to be pretty comfortable with it, and so I would like to see this go through for publication, in due course. I intend to add a little bit on a predictable interruption, which I think people might. I've actually felt like sometimes people don't understand this, but it's actually not that hard to understand. So everything in the solar system that we are interested in tends to be near the ecliptic, the plane of the Earth's orbit, or more exactly, the plane of Jupiter's orbit, because Jupiter really dominates this. And therefore, as the things orbit around the sun, and because the orbit periods are not all 1 year, you're going to have times where any object, Mars, not the moon, because the moon orbits the Earth, but Mars, Venus, Mercury, Jupiter, whatever, goes behind the sun. And that's true for most of the larger asteroids, and many of the smaller ones too. And in astronomy, this is a really old term. That's called a superior conjunction. An inferior conjunction is when superior conjunction is when the object is behind the sun. An inferior conjunction is when the object is in front of the sun. With the planets, only Mercury and Venus can have inferior conjunctions. They're not typically that big a problem with communication, but superior conjunctions are. We've known for quite a long time now, since the 60s, that the solar plasma, which is very messy and increases rapidly, faster than 1 over r squared as you go close to the sun, prohibits communication in any usable sense for ray paths that go sufficiently close to the sun. Sufficiently here means it will vary with frequency, but typically right now for X band and Ka band, 2 degrees from the sun is viewed as sort of the sticking point. And nowadays they typically just plan for this. They don't wait till the communication drops out. They just say, okay, we're going to have a 2-week period. And and this 2 weeks will repeat every 780 days. That's the synodic period between Earth and Mars. That changes. That's different for every body orbiting the sun. So it's shorter for Venus, for example. But it's going to happen. And nowadays the probes are uncrewed, and they just shut them down. They just say, okay, go on standby and just wait for us to come back. And maybe they do something where like the Mars rovers might just resample a surface thing, do a long integration on one of their mass spectrometers or something like that. That's also true, by the way, for stuff in transit to the Mars or any other body. And that actually tends to worry the mission planners a lot, because if you're on the surface of Mars, you might have other assets, but if you're out there in deep space, you're by yourself. see here.
So, Marshall,
We gotta pick
we have cues here. You want to take them, Martin?
Yes, I'll just slow this. This is the basic idea here, and this is the dropout periods for different orbital missions. So I can stop here and take the cue, and that is
Thanks for this document.
12
Martin Duke
minutes.
from Google. For those who don't know me, I'm a Quick enthusiast, and I'm here partly because of the intersection with Quick and with a lot of the work in this working group. Two things that I would find very useful if it was in this document. Number one, the security considerations. There are a lot of like security keywords in there, like certificates and stuff, but actually clear articulating the threat model would be very useful. I mean, there's a bunch of DOS attacks. Like, is this connected to the internet in like a literal sense, where like I can send packets to Mars from my house, that kind of thing. Secondly, an inventory of the existing space networking technology. I'm loosely familiar with DTN and the CSSDS suite, like SkipsDP, et cetera. And it would be great to understand where those are not adequate for the requirements that you've stated.
So you think that the security section needs more details, basically?
Well, yeah, I mean, quite specifically, like explicitly enumerating a threat model. Like, what are the attacks that you're concerned about on this network?
And I think the Moon and Mars are rather different in their threat models. So
That's great. I mean, they could be different subsections or whatever, but that would be very helpful to understand what the design needs to look like. Thanks.
okay, thank you.
Yeah, I think I'm next. Hi, I'm Sean Turner. My only claim to space is that I live near an astronaut. All right. I guess I want
You
to,
live on a planet.
yeah, I want to caution you from trying to rush to publish. Oftentimes we do these use case and requirements documents, and then later on something changes, and then you look foolish, or you end up you have egg on your face, and you just have to go back. It's okay to get done and just let it live, because you may find that things change as you get nearer the end with other documents. I don't know if there are other reasons why you want to publish it early, but like we did.
I'm not saying we should publish early. I agree with you, actually. I just say that I think we need more comment and interaction with the group before we publish. So that has to happen, regardless of whether we want to publish fast or slow. It has to happen.
Eric Green has the responsibility for this one. I'm not so sure that Martin's second point in the inventory describing why existing technology do not work, because it goes away from use case and requirement. It should be maybe another document to be discussed, right? But I think it doesn't fit the use case.
I mean, I will just say that we viewed DTN as like out of scope for both this working group and, as it says in the charter, I believe, and also therefore for this document. And so unless it's a really specific DTN thing, we think, I would push back a little on.
I'm not gonna die in the hill of it being in this particular document, although I think for many of us who are maybe not integral parts of the space community, understanding where the gaps are in the existing body of work would be useful.
I mean, what if we had more about why we think Quick and related technologies are likely to be used, especially for the Moon? Because that is something that we have discussed. I think that's been discussed on the working group. It's been discussed elsewhere.
Okay, I don't want to legislate. So obviously, like DTN has its own working group, and I don't want to re-legislate the charter. But I just think there's existing work on space protocols, and it would be useful to understand what the gaps are. It doesn't have to be in this document, but it could be on the working group wiki. I don't care, but like it would be very helpful to me and probably some other people in the room.
This point, I
All right,
agree,
thank
but
you.
not in this document. My point.
Warren Murray, Google. So I think I agree with both Eric and Martin, except that they're disagreeing. I think it might be useful in this document to have a section noted, this will be removed before publication. But if you're new to the space, you should probably read these other things, or you should be aware of these other things. And again, it can be ripped up before the document's published, but this is where people start reading and they're like, so many words and acronyms I don't understand. So
a background section, basically.
Okay, Marshall,
Thank you.
the queue is drained. Do you have more slides that you want to cover, or?
Well, I was just going to point out about the lunar time. Timing is actually, I think, is a big thing here, and NASA's been charged with developing a lunar time. Actually, that I'm involved with that at some level. The moon, if you just had a clock, you took it to the surface of the moon, it's going to be shifted by 56 microseconds a day, or 1 second about every 30 something years, almost 40 years. I think lunar adjusted time makes sense. This is what the residuals look like. If you remove that, you get a variation of about a microsecond. So if you're concerned, if your network is concerned with timing on a microsecond level, then you're gonna need to worry about this. I think this is a much bigger problem for Mars, where these will be millisecond type things and second changes between. I mean, the moon never goes. The distance to the moon never changes very much, whereas the distance to Mars changes a lot. And there's a simultaneity aspect too, because all of this, you need relativistic models and special and general relativity. Simultaneity is not a general thing. It depends on the observer. And there are, I think, replay attacks that might be done based on that. However, that will not be a problem until we have more than two separate locations with networks besides the Earth. So Mars alone is not enough. But once you have Mars and Venus, or Mars and somewhere else, Mars and asteroids, say, then yes, that will be a problem. So in any case, I just wanted to bring that up. I personally think some of that should go under the IETF Space Research Group, and I'm going to propose that in due course. All right, thank you.
Okay, thank you, Marshall. And I think I mean, even if like this document has got like a lot of comments and all this thing, that when making it to the working group document, I think we're still starting up. So as you heard, Marshall, please review comments. I think we got some today. So those.
Yes, I was not saying that I thought this should go immediately to publication.
So yeah, let's work on it. Get some more reviews and comments, and let's work on it. So next up.
Do I have to undo anything, unshare anything to get?
No.
To drop this?
We're gonna fix it. You can get rid of the video if you want to. But next up is Wes. Padma, could you share, because I was not able to share. Let me do these things. Unshare, share, architecture. I'm gonna give this to Clicker. So you got it, and we'll use the timer this time. So Padma is gonna start a timer, so that Padma, can you do that, or shall I do that? You can start.
Okay. Yeah. Well, good afternoon. I don't have any more physics, so Marshall covered all that. But I'm going to talk about work we've been doing to define architecture for using IP in deep space. Mark and Tony have been working together with me on this. And I wanted to point out right away, there's an item in the charter, milestone for documenting necessary differences that apply to IP architecture when considering space networking compared to terrestrial use. So I was in conversations with multiple people earlier this week where they thought architecture might imply something a little more grand and prescriptive. What we have is actually a bit more descriptive, or descriptive rather than prescriptive. And so it sort of describes all the things you should watch out for and some possible ways to work around them, just like the milestone is asking for. But it's not like an architecture in the sense that it says this is exactly how every single IP system in space should work. It's very closely related to the use cases document that Marshall just covered, so you should read it probably first before you try to go into this document. We've been working on it for a little while. It grew initially out of some of the authors' experience with using IP protocols in space over different types of space links, and also working with Quick and trying to see how it might apply to deep space usage based on some of its unique features and capabilities. And then the need really arose when, as Marshall was covering, there's been this increased set of commercial and government plans to roll out larger scale networks that include IP around different planets. The original draft was part of the Deep Space BOF, and this is second time since then that we've been presenting on this. The topics that we cover in this architecture start out at the link layer and talking about the types of links that IP has to run over for the deep space environment. This is a bit different than most of the cases we have terrestrially, but it's also not that complex. And there are well-known and understood standards for running IP over these types of links. So the IETF doesn't have to invent anything new here. We use existing IP over CCSDS technology. And then when we're running over links on a planetary surface, they're just IEEE or 3GPP, so this is also well understood. Then we get into, in section 3, some more specific description about internet protocol and how inherently in the internet protocol, there aren't timers and things that will break IP's use in very long delay environments. And we talk about in the current version how store and forward is actually possible. And I'll just mention, I have a issue I just filed yesterday in our tracker to actually try to find better terminology here, because what we're talking about is not store and forward in the same sense as DTN, and the store and forward term itself is probably overused already anyways and confusing. So I want to try to get rid of that, but essentially we're trying to describe how IP itself doesn't really care about delays. Then the architecture is trying to address questions like, for deep space use, how will IP addressing potentially work? How could routing potentially work? How does a transport protocol need to be configured or tailored? And what else would an application need to do special in order to work in this kind of a system? So top of the stack to bottom of the stack, what do we have to do in an IP-based network in order to function in deep space? And I think this was a chart I used at the BOF to explain the situation. And maybe hints at what Martin was asking for earlier, in that there are different protocol stacks that exist. The incumbent sort of dominant way of doing things is at the frame layer without real networking. And so there are a lot of applications that write data directly to link layers, and the world is starting to move away from this because scalability and all of the kind of mission complexity things that Marshall talked about break down when you're trying to only operate at the layer 2. And so for that reason, there are network approaches, and IP stack exists as one of those options, which is what we're addressing in the TIPTOP group. And it will run over the CCSDS data links the same way as a DTN stack is able to, and provide a networking solution. So specific to the IP stack, what we're really talking about so far in the architecture document is focusing on the use of quick transport over UDP. And I think that's a easy choice to understand, since Quick is our most modern, fully featured transport protocol and easier to modify and work on than TCP. So if we need to adapt things for deep space, Quick is the easiest thing to target and to work with. And below Quick, we would envision supporting both IPv4 and IPv6. And there could be things on individual hops used like header compression. and maybe some flows would even be able to use IPsec if that was useful for them. But I think more important is not actually these protocols themselves, but the things around the protocols that complete the architecture. So how do you set up this stack, getting IP addresses, doing routing, how does quality of service work, how will network management be performed, what security mechanisms are feasible. I think that presentation later on about alternative approaches to security fits in well with this kind of architecture discussion. And then I mentioned planning and scheduling here too, because one of the most important things to understand about these networks is that they are heavily planned and scheduled. So this is very different than the internet. So some considerations that we have in defining the architecture are the needs to accommodate and exist within the whole ecosystem of existing space data link standards, along with the emerging set of standards that are being spec'd for use on the surface and in orbital regimes around the moon and Mars. So there are different sets of documents from other standards bodies or industry groups that we want to be compatible with the IP architecture that we're defining. And those help define the context this architecture exists within. The hope is that if you are more of a networking engineer, you can understand the IP architecture document we have, and you don't need to go and read the thousands of pages of this other stuff, but you can trust that it will be compatible. Just to give a little bit more context, I don't know if this is legible, little, but to help supplement the kinds of things Marshall showed in the use cases, this architecture is intended to accommodate multiple service providers existing and being able to provide connectivity between the Earth and other planets, as well as just local around other planets. And this is a diagram borrowed from a Moon to Mars network architecture document that NASA has published. And the important things to take away are there are multiple commercial systems and multiple different countries that are helping to provide connectivity. And so the architecture itself should work with multiple providers and be compatible with the types of different considerations that arise from these kinds of systems. Since the last revision, we've done some updating, and I'm actually presenting today, I think mostly because I'm guilty of making the majority of the updates. What we changed most since the last version that Tony presented at the last IETF meeting is we added a section on transport protocol considerations. And I think Mark asked me to add some content on transport. And he was probably expecting a paragraph, and I put 4 pages in about here are a bunch of reasons why it's hard to use existing internet transport protocols. These are general considerations though. And so we actually have a separate quick draft that describes specifically how to configure quick related to these general considerations. And I think the idea is that in this architecture document, since it's general considerations, we could apply the same ones to other transport protocols if needed or desirable, or even new transport protocols, and they would be suitable for deep space use. So this is the list of considerations that I had come up with, and they actually, it looks like quite a list of things, but they fall into 3 broad classes, in my opinion, of ways that you mitigate them or work with them in the deep space environment. And so the first class of things I group together are things that happen typically in the beginning of transport connection or an application flow. And by those, I mean like feature negotiation, initiation of the transport control blocks and establishment of transport state, and probing of what features are supported by the other side. And the way that we would see mitigating challenges that these things pose in a deep space environment because of the conversational nature and the send and then wait for a response nature of these mechanisms, we would see getting around them by tricks, I guess, carefully planning and scheduling things, orchestrating things so that you know in advance what to expect and what's supported, rather than having to dynamically determine it on every single connection. Also, pre-establishing information and making it long-lived at a node so that connections can be remembered across different connectivity events. That will help to prevent having to wait 40 minutes handshaking just to establish the same sequence numbers and start talking. And these things, Mark has done proof of concept with his quick implementations already. Additionally, there's a class of things that I've grouped together which occur during the connection. Usually transport protocol is continuously probing these things and or waiting for events to happen and sense them in order to respond. And here I'm talking about retransmission behaviors, handling of failures, doing the typical congestion control loop, and path MTU discovery. Sort of similar to the case of the prior things, since a lot of the network is scheduled and well coordinated, things can be known in advance. And so instead of dynamically probing and trying to make good guesses, you can actually be certain ahead of time about proper values to use for some of the parameters here. And so the suggestion in the draft is to use sort of time-based or scheduled sets of parameters rather than closed loop algorithms that dynamically try to adjust, and to use resource planning to largely avoid congestion and corruption losses. And then the third class of things I think are more in the boundary between how an application uses the transport protocol. And these don't need to pose a problem necessarily, because applications won't use them in deep space in exactly the same way that they might use them in the internet. And they're sort of optional aspects of a transport protocol that you don't need to use anyways. If you wanted to use them, the algorithms underlying them could be adjusted for deep space as well. And this class of things I included multi-streaming, multipath transport, and FEC at the transport layer. So the next steps, I think we want to advance this towards working group adoption, but I know we haven't discussed it as much on the list as the other document. And so it's needing more attention. You may have some comments. I already have 2 issues in myself to make some changes, and we would definitely be interested in other people's view of things and whether you think this is scratching the itch. There's a GitHub site which you could put issues in at, or of course discuss on the mailing list or here today. And I think that's all I've got. So we've got 8 minutes for comments.
Thank you. This is cool. So I'm walking in a little bit late. shut down any of these questions or comments, but some of it is just clarification, but one is I'm just gonna try and poke the bear a little bit. So the first one is, do you imagine, for example, people setting up MPLS tunnels here? So you're happy with, okay, that's fine, that's good. Then here's the tricky one: is there any reason we shouldn't require IPv6? And then opens up nice things like Lisp and ILNP and other, like, right, that might give you some of the features that you would want in a place like that. We could just say no IPv4 to talk to space. Shut it down.
I think Tony definitely wants to answer. I think it's a policy kind of thing, though, myself, rather than a technology thing. We could make IPv4 work. We can make IPv6 work.
I mean, you want to tunnel over IPv6 and you want you to do something silly, you got private space on the moon, but I think this is an opportunity actually to really move the needle.
You're probably not in the mic, but
having IPv4 very likely will cause us more trouble than anything else.
Several points. First off, we don't have any authority here, okay? We don't get to dictate what the space agency is going to do, okay? If they want to use X25, they can do that, okay? So we don't get to say you can't use IPv4. Second point, there's some advantages to using IPv4. I'm sorry, but it's true. This is bandwidth restricted situation, right? We're no longer talking gigabits, we're talking modems, okay? So the extra header, the extra overhead matters. And so they're gonna have to make a really tough call. Now, are there benefits to doing MPLS? Yes. SR might be very useful, okay? But, you know, it's up to the agencies to figure out what's up. And we can certainly put good words in the architecture document to try to steer them, but let's not try to set mandates because that's not going to stick.
Thanks.
Marshall?
Can you hear me? My question, I put it in the chat. If you can't hear me, is what is the difference between multi-streams and multi-path in the architecture?
yeah, in Quick, you can separate multiple streams of application data on the same connection, but it doesn't mean that they'll necessarily use multiple paths across the network. So those are two different things.
Okay, so they're just separate things. I mean, I think a common use case will be multi-path, where you have a high bit rate and a low bit rate, and you want to fail over to the low bit rate. An omnidirectional antenna, say, as opposed to a directional antenna. Thank you.
Yep.
I guess that's me. Jad Hasham, RIPE NCC. Thank you for the presentation. I do have a question related to the allocation of IP addresses, because this is mentioned in the paragraph 4.1, and I quote, address space for outer space should be managed by an RAR, and blocks of address space should be allocated for each celestial body of interest. Now, working for an RAR myself, we have a vested interest. I would like to know if you have further thoughts on this. Are we talking about one RAR? Are we talking about all RARs distributing or allocating these addresses? Also, something that you should consider is that within the RAR communities, it's the community that sets the policy how these IP addresses would be allocated. And not to piggyback on what Marwan was saying, except in very, very, very specific conditions, we don't have any IPv4 addresses to give out. So I'm not saying that it should only be IPv6, but I also would not like to find myself working in an IPv4 transfer market for deep space as well. So I was wondering if you have thoughts on this.
Tony does.
All right.
Tony, yes. Yeah, I added a lot of this stuff. Yeah, we would like to see some kind of address space aggregation in space for the exact same reason that we have address space aggregation here on Earth. It's very helpful to routing for us to be efficient. And in the millennia to come, as we populate space, we'd kind of like to not be doing everything with, say, host routes, right? /128s for, a billion different space entities would be a bad thing. Okay, so we'd like aggregation to happen, and we'd like to kind of start doing it now. So how do we get that to happen? Well, the root of that is to do address space allocation for particular clusters of networks. And we've talked about this incessantly 30 years ago, and we're just bringing up the same points again. We've got the ability right now to say, okay, here's what our address space aggregation plan is going to be. Regarding IPv4, I was not suggesting that you do hand out blocks of IPv4 address space that way. That this is much more oriented towards the V6 space.
All right, so maybe just a suggestion, if you want the RARs to be involved in this, maybe you should also take this conversation to the RAR communities, come to the RIPE meetings, etc. So start floating these ideas because eventually the RARs will operate based on the policies developed by their communities. So maybe starting early there is a good idea.
I think that's a good suggestion to take on. Thank you for that one. So for the queue, Martin, you go on, but for the queue, please keep it short because we're kind of running out of time.
Martin, do Google again. Thanks for this, Wes. I think this helps quite a bit. I remain. It's not an easy. I'm asking questions of an easy answer. I think we can start having a discussion about this. I'm having a little existential dread in that you're describing. We're using quick, but there's not really congestion control. We're not really having a control loop, et cetera. And like at some point, it's not quick. Now you've sort of articulated the need to, apps in the world are being built on top of IP and quick and what have you. And so maybe you're asking for the API, but at the same time, there's a document how we need to change the API. I said DTN, which caused everyone to go into a blackout state, and I'm sorry about that. I didn't mean that. I said something else because a long time ago I worked something called SCIPS TP, which is a CCSDS transport protocol that was designed to solve a lot of these problems. And I wonder if what you really need is just like a multi-streaming API or something on top of something like that. Or something. Anyway, I don't think we have time to reply, but I would love to have a dialogue about this.
I know it well, so we should talk about it.
Great. Okay. I mean, I'm here to. It doesn't sound like, but I'm here to help. But I'm having trouble grasping what you're actually trying to.
But your biggest concern we should address further in the document, which is that this looks like quick on the wire, but isn't quick.
Yeah.
It's different than quick for the internet, so we should talk about that more specific to quick. In this architecture doc, I was trying to be general about these are the considerations for transport.
Again, I'm making more broad comments that maybe isn't going to be solved in this document, but
yeah.
I have a lot of. I'm failing to understand the
purpose. This is the real work for the working group. So
okay, all right, thank you.
Good. Okay, please be short.
So +1 to what Martin said. However, you don't talk about anything cross-layer, not even DLAP type stuff where you know stuff about the link, and you don't also speak about how much capacity you might have, which you all must know. So it seems like there are things missing in this picture which I would have expected to see in a radio-based communication network. Do you think that's relevant?
Yeah, I think we could definitely expand on that. Yeah.
Lars.
There was Lars. I got so 3 quick points on the point that Marvin raised in terms of V4 and V6, right? I'm not aware of like large swaths of unused V4 space being available that we can use in space. So unless we want to put nets everywhere, I guess it's sort of naturally the answer is V6. I don't kind of, as much as we might want to prefer it. Otherwise, anyway, just as a data point, and maybe I'm wrong and there is V4 space available or nets are cool again. Anyway. Point 2, +1 to Martin, right? You can only call it quick until a certain point, and then it's not quick anymore. And in the run up to this, right, the pitch was, there's a few easy tweaks we can make, and it's going to be quick. That is sort of now looking slightly different. That worries me as well as a quick person. And third, the multipath thing triggered me actually to click the button, which is like we don't really have a functioning multipath transport for the internet at the moment. We have things that work in some deployments. Space is very different, and so I would sort of punt this to future work rather than like making it look like this is something just around the corner.
That is actually the approach. I may have misdescribed it.
So sorry guys, I have to cut the queue. I mean, please take that one in the mailing list or GitHub. There are very good comments. Please create the issue, right? And have discussion there also in the mailing list. So Mark, you're on. Thank you. Thank you, Wes.
Thank you. Good afternoon, good evening, good morning. Back to just a comment on what Martin was saying. Yes, we know quick is, there's more work to do. We done some work, but I guess we have been saying that we should spend the whole meeting at some point on transport. Okay, this is about DNS. This was presented DNS up some time ago, I think 3 or 4 IETF, but that was at the end of the last session, and the meeting was late, so I had like 2 minutes to present and no questions. So it was kind of presented to the DNS up, but not that much. So how do we use DNS in deep space? The key thing here is obviously DNS resolution from deep space to Earth and reverse is to be avoided because of long delays and intermittent communications. So you need a local autonomous naming environment on the celestial body networks with all the useful names, so that essentially every name used on this celestial body network is actually resolved locally on that network. It should be secured at a DNSSEC. Well, unless we decide to have a completely different route and a new trust chain and the whole shebang, which I suggest we don't. Therefore, if we're using DNSSEC with the same route, then we need to do DNSSEC validation on the celestial body network, which means that you need to have everything there to do your validation, which is the old trust chain. We assume that the management of the DNS servers and zones will be done from Earth. I'm not sure I want the astronaut to configure his own files there, at least not yet. And especially for Moon, it's not far-fetched thinking that the Moon network may be somewhat directly connected to the internet quote code, in a sense that it's so near, and there are already some providers planning to have constellation of satellites that will provide mostly full connectivity. Given it's pretty near, what I'm trying to say here is we need to avoid name conflict. So by using the same route, same trust anchors, same delegations, it should be straightforward. I'll be using local for meaning celestial body network infrastructure point of view. So I run a brainstorm with some people in the DNS environment, and I see one of them here. And caveat, everything here which is wrong is my errors. So I will name them for giving the credit, but point to me if I'm saying wrong things. So all the approaches are essentially you pre-walk all the names you will be using on the local network. You pre-walk them, and we'll see how a more detailed discussion on it. Or you prefetch all zones and then you send them to the local network. Or in a variation of those is you do a special zone with only the names you need. And there's obviously a few others. All approaches kind of share similar setup. The current draft doesn't go way into details of everything here on purpose, in the sense that there's work, additional work you recognize. We will need some kind of a DNS local infrastructure, either or both authoritative NS and resolvers, trust anchor preloaded, some way to send the data, the zones from internet, from Earth to there, to Moon. Again, I was saying local use names are in the normal DNS tree. Clients will use local resolvers, and we should be inspired by RFC 8806, which is the running local DNS root servers, RFC. So suggestion from Warren. Thanks, Warren. And again, all errors are mine. You pre-walk all the needed names that you need, for example, on Moon or Mars. You do a 3-walk of all the local names you need with DNSSEC related RRs. You save all this and then send it to the local infrastructure on Moon or Mars by some means to be discussed in a second. Caveat is you need to know all the required names. You should not forget one. So if you forget one, then application will just time out on DNS resolution. Second approach, you prefetch all zones of the needed name hierarchy. You carefully choose name hierarchy. Is this going to be a new TLD .moon, a second level, I don't know, in.moon, or moon.spaceagency.int, or those kinds of things. You choose your anchor in the tree. You need to have access to those zones. Therefore, if there are multiple providers and multiple users and stuff, they may need to do this work separately, or have someone who kind of have access to all this and send it. Yeah, if it's not a dedicated name hierarchy, then a lot of non-useful resource records will be uploaded, which is kind of a waste. 3, that was suggested by Mark Andrews. I don't know if Mark is here. Anyway, credit. Again, all errors are mine. You, from a current zone, say, I don't know, nasa.gov, you only select the needed resource record and create a special version of that zone with only those RR. You sign it with the same key and then send it to the local infrastructure. That requires to carefully manage both versions of the zones. So pros and cons again. Obviously, you could do local zone split DNS, but then if it's managed, the whole celestial body network is managed by a single provider, then that could work. But we already have plans to have multiple providers, multiple users, and multiple networks. That might not be great. So it might be okay for early deployments, but on a mission-by-mission basis, but doesn't scale well and doesn't support well the local interconnections of networks. So how do you send zone files, or the files, the collection of files you need to deep space? Our typical ways, for example, for zone files, is to use DNS, AXFR, IEXFR, rsync, FTP, or DNS over TLS. All those use TCP, which is not really suitable for deep space. You could do AXFR and IEXFR over QUIC. This is RFC 9250. So that could be one way. Might be others. Obviously, you do your own, file transfer. Now the elephant in the room. Every time I was talking about this, they say, people come in and say, we should have a new TLD, or we have, So what I just described up to now is roughly doesn't care about what's the hierarchy. Obviously, the chosen hierarchy will have some impact depending on the approach, but so should we have a new route? Then you would not use the current trust anchor. Then we would need delegation policies. To me, it looks like a can of worms. Uh, while it may be tempting to define moon and Mars, moon, Mars, it still requires quite a lot of policies and delegation trees, and we'll have a lot of gray zones. What the spacecraft cruising in the space will have what? And the spacecrafts at Lagrange points will have what, right? So my suggestion is the owner of a service or host just define the names within his current name hierarchy, and then you make sure that zone with that list of names is currently cached in the celestial body network. Example of these would be habitat1.moon.spaceagency.in and things like that. Right. Other approaches, don't use name, only use IP addresses. Obviously easy for early deployments, and that's probably going to be the case initially. Caveat is some application protocols don't work so well without names. You could always go around, but use a static file distributed by some means. The famous host.txt doesn't scale very well, especially in multiple networks, a network of multiple networks and users. The current draft is, I would say, incomplete. More details about RRs, which are TTL considerations, zone signing. There's a lot of important details or important stuff to be added. But it would be good if we get here, and most likely with the DNS Hub or the DNS Directorate or someone, kind of have an approach that is chosen or recommended. I'm not sure we want to go through all these and keep them. Maybe that will become the case, that we don't want to choose for people and they will just use the one or the other. So that's my presentation. Questions? Warren?
Warren Kamari, Google. Just to add some sort of additional flavor or context, these approaches aren't really in conflict. It's not that we have to necessarily choose one or the other. Many of them are just sort of evolutions of other ones, or sort of staging to get from one to the other. Yep. Like, for example, the first one, you can run a device instrumented, watch what queries it do, shovel those into a thing. Approach 2 is for sort of a larger scale, and they're kind of in order in terms of sort of how you might deploy this. The last thing on let's choose a new name, that's like the world's largest bike shed. You could spend an infinite amount of time on that.
Thanks. So, summary, we should not choose an approach, but list all of them and how to do this. Okay, sure. Lars?
Lars Eckert. So I got triggered by this presentation, but it actually applies to the following points on the agenda as well. So I think we're still sort of thinking we're in buff phase, right? You had things on there that are already answered by the charter, right? Using IP addresses is not compliant with what's written in the charter. The charter says we're going to use DNS and we're going to tell you how to configure it, right? So we don't need to spend time on discussing anything else. It's going to be DNS. If it's not DNS, then we need to close the working group and recharter something else that doesn't use DNS, right? Likewise, charter doesn't talk about email. We have a presentation coming about email. I don't understand why, right? Shake, not mentioned in the charter, arguably related to IP, probably not part of the IP that's deployed on the internet, therefore out of scope. Same thing with changing the security handshake for Quick. Not part of Quick as it is, right? If we want to do this, it's certainly not in this working group. So I really think we should really focus on what's in charter, which was the initial required things to get something working in space, and punt off all this other stuff to later. Because I think we're just wasting discussion time that we could spend on the earlier presentations where it would be more needed.
Lars, I think that's a good suggestion. I mean, we have been also chairs. We have been also talking about how to progress. But at the beginning of this session, I think there's some benefit of taking some of the how people want to use this space network so that we get the requirement and the use case right. So that's why I think it's fine. But I personally agree we should focus a bit going forward. So. If there is no question, Mark, you also have the next slide. So we can start with that one. Let me share it again.
Well, just a comment, DNS was actually in the charter. I agree with the email, but I think this, the co-chairs put this as non-chartered items.
So also, maybe we can just use 5 minutes for this one.
Sure.
Yeah. To catch up.
Sure. So Pete is listed here, but he agreed to be co-author on the draft, but the current draft doesn't list his name. Next version will be. Okay, so sending email from Earth to deep space and back. Again, we have network deployment plans are that IP and 5G Wi-Fi IEEE connected network on celestial body surface. Deep space are point-to-point links, and our email protocols are SMTP and IMAP and POP and DNS and HTTPS when you read your mail on the web. Our email protocol, SMTP, is used for email submission and between servers, uses TCP, may use TLS, is chatty, so you send hello, you wait, you exchange capabilities, you send mail from, okay, recipient to data, so that's multiple round trips, so not very suited for deep space. So recommendation, don't use SMTP on long delay deep space links, use another method. IMAP and POP is for users to get their email, uses TCP, may use TLS, don't use IMAP, POP on long delay deep space links, but you could use it on celestial body surface networks to the local server as on the internet currently. So how do you transfer SMTP things or mails over deep space links? The flow, suggested flow here is the last SMTP up server on Earth will actually convert the mail into a batch SMTP MIME object. That MIME object will be sent over HTTPS or essentially HTTP3 with ProfileQuick. The first server on the surface network will receive the MIME object via SMTP, then forwards it locally as usual as SMTP, and the users will read email by connecting IMAP over connected IP network on surface network. Obviously, that's kind of for new mails. I guess, how can I say that? I'm not sure we want to really suggest to fetch all the old emails you have since 30 years on the surface. One thing here is how you discover the next up, so the server on the moon or the Mars. You could do by static config, which is probably going to be good enough for quite some time. I had that draft being reviewed by John Levine. I don't know if he's here. Thanks, John. He was telling me, well, but you may want to have, multiple servers, backup and stuff. But MX records point to a name, a host name, where here we're using a URL to actually access using HTTP to, an endpoint. So in this case, you could use instead URI DNS resource record, which has essentially the same functionality as MX record. So you have weights and you have priorities. And then instead you use, you point to the endpoint, the URL endpoint of the servers, email servers on Moon, for example. And that's an example. That way you could have the last up SMTP server being essentially not configured statically for the next step. DNS, well, if obviously email use DNS, so configuration discussed in the other document. Anti-spam, you may not want to have too much spam sending over deep space links. BSMTP means that you have no capability negotiation in SMTP. So it needs to kind of agree or configure capabilities between the two ops. The current capabilities, I haven't listed all, but the current capabilities should be no-brainer, but more work has to be done on this to research what needs to be done. And I think that's it. Looking for comments or questions. And again, thank Pete for agreeing on being co-author, but currently all errors are mine.
Hi, Marwan, Cloudflare University of St. Andrews. I can really appreciate people are spending time thinking about some of these issues, but let me, sorry.
Yes.
So I can really appreciate people are spending time thinking about a lot of these things, but again, let me push back and say, why should we use email at all in space? I mean, I can imagine a messaging system is one way, it's like it takes care of a lot of, and it does away with all of these other things. I get that NASA wants to do whatever we've been doing for a long time, but we don't put turbine engines and aerofoils in space. We've had to rethink food in space. I think we are at a stage now where we can take the existing technologies, manipulate them in ways that still give people on the planet what they want, but aren't the same thing we already have. And at the IP layer, there's a lot of room to maneuver. We should really, really think about it.
Mm-hmm. Sure. But messaging has been said as a key thing that we need to provide.
Although it is an application, so I haven't read the chart, right? But email comes with all kinds of assumptions that are not in space. Let's revisit the assumptions and build with those about space.
Well, have you read the draft?
Admittedly, and this is why I said I walked in late, and I'm happy to be shut down on anything I say.
No, I'm not saying you're shutting down. Please provide comments on.
Absolutely, thank
you. Okay, so thanks, Mark. Alex, right here. So we saw like in Wave's presentation, there was some header compression somewhere in the slide. So we're going to talk about the compression. Let me see if I can find, yeah, there you go.
Yes, and the clicker.
The clicker thing to you, okay?
Yeah, that will be important. So, hello everyone. My name is Alexander Pelov, and I'll be presenting to you the applicability of this thing that is called SCHC, which is very unpronounceable as it is, so we call it SCHC. So I'm co-chair of the SCHC working group, and this is basically just an overview of things that we've been doing at the working group, right? And I'm going to start with what is SCHC. So SCHC stands for Static Context Header Compression, and it is a framework that deals with compression and fragmentation, right? For the TIPTOP work group, I think the compression is the one that is really the main topic. So I'm going to only to be talking about the compression here. And I just want to say that it's a technology that is right now like 5 years old. There's an RFC. It has been adopted by other SDOs. There is an IEC standard, DLMS, LoRa Alliance, and so forth. There have been several industrial and open source implementations deployed in critical infrastructure and operating for many years now in smart electricity meters and smart gas meters. So that's the first thing, like it's something that is out there and it's working. A second point is that the way it was designed and constructed, it was designed it started from the LP1 working group, so for LP1 networks. Very asymmetric networks, very constrained, like there are networks that were operating at 100 bits per second and having something like 1% duty cycling. So we were able to run SCHC on this type of networks. And in the same time, today what we have is we have works that put SHIC on 5G networks, underwater acoustic networks, ultra low latency millisecond networks like that have a latency of up to 1 millisecond, and mesh networks for 6LoW and so forth. So basically, SHIC was designed as a framework, and that framework is basically, so we define the Lego pieces, and whenever the use that you want to have, it is like you build your own object with these Lego pieces. And it turns out to be extremely flexible. And you can really apply it to the specific, it's not tied to a specific technology, it's not tied to a specific use case, right? So in the core, there are two really very important properties of that technology that I think are very relevant to the work of the TIPTOP working group. The first thing is that it's a stateless compression. So that means that you can configure once some shared information on both ends of a link, and then this information doesn't change, and all the traffic between it's compressed in a stateless manner. So that means that if you lose a datagram of your data or 1 million datagrams, it's not going to break your compression, you're not going to lose synchronization or anything. It also means that it is RTT agnostic. So if your thing requires 0.01 millisecond between the two endpoints, it will work. If you have 1,000 years of the RTT between the two endpoints, it will work. Right? So I think that these two properties are super important, right? And also it is with a very low computational complexity. So theoretically, you can run like gigabits per second with that. Now, I'm just going to show a very simple example of how that works. So here we have two celestial bodies, and it's a very simple example, like for the satellite people, like the interplanetary people, like I'm really simplifying things. Don't kill me if I've made some mistake. So here we have basically the SHIC compressor and the compression and decompression that's happening on the satellites. And the pieces of shared information is the pieces that are here, right? So it's the exact same information. We call that the SHIC context. And here you have like a small cards, you see, so we call each of these cards a rule. So they are numbered 1, 2, 3, 4, 5, up to the number of rules that you want. There are technologies that have 1 rule, there are technologies that could have 1 million rules. That depends on your traffic, that depends on the things you would like to compress. Now the example goes like this. Say you have an IP UDP quick packet. It goes to the compressor goes, like in this example, we are going to be compressing only IP UDP. We can go further and it can compress other protocols, right? This is just an example. So there is a matching operation there, and see that we identify its rule number 2 that is going to be used for that compression. Over the air, like over the vacuum, is going to be sent like the number 2, so the rule that was used for the compression, and the residue of that compression, plus everything behind that remains unchanged. So that's received by the other end. The decompressor says, oh, I need to use card number 2, so rule number 2 to decompress. The residue is used to decompress the IP UDP header, and the packet is the same as the one that was being compressed, so it's processed by the normal IP stack, and it is then forwarded down to the moon surface. Now, that being said, there's some very important thing here, and that is that the definition of a rule and the definition of a context was formally defined. So there's an RFC on that, and it's a working thing that's getting deployed. So here we have an example of one single rule that is being expressed. So for example, for rule ID number 2, these are the fields that we're going to be compressing. So these are some like the size of the field, like IPv6 version is 4 bits. These are for bidirectional communications. We can have rules that are only in one direction or the other, if you want. These are the operations we are going to be using to actually see if that rule is able to compress a given packet. So these are called matching operations. And these are the actions that we are going to be using to compress and decompress. So that rule contains all the information that is necessary to see if a rule can compress a packet, to indicate how to compress it, and to indicate how to decompress it. It is a static one, never changes. It is shared between the two. And in case the size of that table scares you, in byte size, it's something, it's less than 50 bytes. It's typically 20 to 30 bytes. Right? So pretty neat. So why do this, right? Well, I think one of the examples was like IPv6 is too big. Well, we can compress IPv6 very, very well. It can go down to 1 byte, right? So that's in good conditions, right? If there are some crazy conditions, it can be 20, 30 bytes, right? But it's really efficient. IPv4 as well can get compressed. And like the really nice thing is that in the rare case you cannot compress anything, well, we just send the IPv4, the IPv6 traffic, and nothing is lost here. So I have 3 minutes, and I'll try to show a very short example of how that goes. So hold on to your chairs because it's going to be a little bit fast. So this is a short, quick exchange on Wireshark. Now, first, that's an example of a rule that doesn't match, but I'm not going to go through that. So here on the upper hand side, you have these are the IPv6 UDP header. So these are the bytes, and there is a parser. So the parser is going to parse the bytes one by one here in that example, but an implementation can do the whole operation in one go, right? So this is just because we are limited humans in this room, right? So with the parser will look at the first 4 bits. And the operation to see if that is successful is equals. So are the first 4 bits equal to the thing that we have here, which is 6? Yes. Then we move to the next one. Are the next 8 bits equal to 0? Yes. Then are the next 20 bits equal to 0? Yes. And then we have 16 bits we just ignore because that's a thing we know how to compute. And then on by on, we just compare one by one all the fields. And if all the matching operators are successful, then yes, we can use that for a compression. So rule number 2 can be used. Now we can actually do the compression itself. And for this, we look at the next column. And it will tell us how to compress the thing. Well, the first field is not sent. We do not send anything. We do not send anything. We do not send anything. This will be computed on the other side. Here we need to send, like this is the host ID, like part of the IPv6 address. So this one we need to send. And here for the example, we need to send like the 14 least significant bits of the UDP port. And so in this example, we have our 48 bytes down to 10 bytes. Now the decompressor, well, it goes the other way around. They receive the packet, they say, oh, it's rule ID number 2. So these are the data I've received. I look in my rule. Okay, the first 4 bits, they were not sent. So I'm going to take them from my context to reconstruct. Then one by one, I take everything from my context that was not sent. Things that were sent are put there. And so, bingo. It's magic, almost. So that thing, like this is thing that you can start and it can work today. The interesting point is that these static contexts, they do not change at all with the data, but you can have a secondary process on top, like a management, which you can add and which can be, so there we are working on that on the working group. If you use netconf, you can use netconf for that. In the energy business, they use DLMS. DLMS use their thing for that. So this can be decoupled actually and can be made specifically for the TIPTOP working group requirements. So I think it's a really important point to have this discussion between the 2 working groups. And the way I think it could be really simple to work is, hey, we have these requirements from the TIPTOP working group, like this is the frame loss rate, these are the RTTs we expect, these are the characteristics, and the SHIC working group can very easily provide a profile of something that's working there. Yes.
Gori, individual again. Super keen on this sort of thing because I think it's exactly what matches the space requirements for efficiency. You mentioned quick rather than skips-TP. Skips-TP I could compress down using this technology to a couple of bytes. Quick as a 40-byte header that's encrypted. How do you see that fitting in?
Okay, so actually we can, so in the opening of the connection of the quick, you have this connection ID. So we can do stuff about this. Like, for example, on the first packet, we can indicate, hey, well, take this into our memory and keep that. So we can do that. There is actually a document that was started in the working group where people are saying, okay, there's the outer header of Quick, and maybe there are stuff we can do inside, right? But that thing really needs to be adopted and worked on with the Quick working group, right? So I think we need to separate the two. There is the quick win and super easy thing to do, IPUDP Quick, and the inner thing it's, with the Quick working group.
Yeah, fun. It's an extra piece of work though, isn't it? Yeah.
Yeah, exactly.
Juan Freire from INRIA and D3TN. So quick question, to manage these rules, I guess you need to ensure some consistency across the network, right?
Yes, yes.
And this means that likely managing this in a space environment will need you to have time tagged rules to which is the time frame on which such a rule is valid, so that when you provision them, all of them tick out and start to be valid at the same point in a synchronous way. Is this more or less what you have in mind?
So the way it would work as of today is like they are provisioned and they're eternal. So you don't have problem of synchronization. But we have works in the working group that say, hey, you can manage them. You have this time synchronization. This rule is valid from this time to this time and so forth. We just don't want to come to the working group here and propose stuff that maybe do not correspond to what the working group here is expecting. So if the things that you are saying are expected, we'll be very happy. I mean, we have some ideas around this. It's very easy to do, but our point is to actually bring solutions to a request from this working group. But yes, exactly. That's something like, well, you can shoot, and like here I'm going into a more, how can I say, solution mode. You can say, well, you send a packet that's from, let's say, from Earth to the Moon, to Mars, and you say, I create a rule, and that rule compresses an IPUDP quick header with some quick identifier, like a session identifier. That rule is valid for 10 minutes. And during these 10 minutes, so this thing is flying over to Mars, right? I'm actually sending compressed packets, and after 2 minutes or 1 minute and a half, I know to stop using that, right? And then it will expire, and everything will arrive like in 20 minutes, and it will happen gradually. But these things, like, we need really to be working with you so that we know that we are not going into uncomfortable area for us, right?
I mean, something that just quick thought here. So it's interesting use case where you ship the rule configuration ahead on the front, and then just a train of packet compressed by such a rule, and you just apply that rule to that bunch of packet, for instance, and then you get rid of it.
It is possible. So it is possible. Yeah.
Makes sense.
And just to tell you how we worked actually in the past with the working group so we had these champions of the different technologies that came and they said, this thing makes sense to us. So the working group actually was working with these people from these technology vendors or technology associations. And when we had ideas, these vendors, they said, that makes sense to us, or that doesn't make sense to us. So if things like this make sense to us, we can, like, it was presented, but we didn't want to push any solutions here. Right?
Makes sense. Thank you.
Sure.
Okay, Eric Wang, the responsibility for both TIPTOP and SHIC. I am lucky. But indeed, this is basically how SHIC works. So I think this is the sole presentation, most probably, of Alexandre to TIPTOP. But if the group in the requirement and use case say, yeah, that's interesting, it will be done in SHIC. It's completely out of the charter of this working group, but completely in the charter of SHIC.
Yeah, right. Alex, yes, thanks. I don't think anyone there. So thanks for doing this, and we'll be in contact, definitely. Thank you. With that, we're right on time. That's thanks for all the presenters to doing a good job right now. And then Britta, you're up. Let me share the slide. So we're going to talk about some securities. I think the discussion here would be more focusing on like what TIPTOP on a space, how the security could look like, or what are the pitfalls and other things, rather than a specific solution, just to be clear. So let me share.
As the last presentation at TIPTOP, I'm tempted to say that there's the TIPTOP presentation.
It's
mandatory, yeah, I have to say it.
And I understand you have 2 presenters, so but you can use this one.
Okay. Oh, excellent. Yeah. Okay, so mandatory statement. Everything we say is our personal opinions. We'll have a joint presentation here between myself and Raphael. talking about different aspects on the security. So a little background. This was discussed the last IETF, and it was a very short presentation, generally pretty high level because of limited time. And at that time, the general consensus was, let's go take it to quick because it's a discussion on security, and we go to the security working group. But the quick chairs asked for more feedback from TIPTOP, hence we are back, and are looking for that from this group so that we can continue in one way or another. All right, so some background. I'm not going to go too much into the details of functionality in space because we already had a beautiful explanation on this from Marshall earlier today. However, just to set the scene very briefly, once again, in the space setting, we are dealing with a lot of latency. We're dealing with delays and packet loss, attenuation. We are dealing with things spinning around planets and therefore being disconnected at various times. And all these actually affect the functionality of our protocols, no surprise. And this starts getting into a little bit of how we fit protocols that are designed for terrestrial uses into space. And particularly when it comes to quick, that was defined, again, with terrestrial uses in mind. And some of these weren't quite accounted for, which begs the question of how are we accounting for them now? Okay, quick recap. Quick handshake, we have one round trip, fantastic. Bunch of parameters goes back and forth. This is actually the TLS 1.3 handshake, so there's not a designated quick handshake. It's a TLS 1.3 handshake that's slotted in. Quick is very nice in that respect where it can pick up from the prior work. There's also a 0 round trip transmission option. So there's a mode that essentially is a pre-shared key. It recovers from the last state and continues encrypting data. So it's not an injection of new randomness. It's very important here. It is continuing from the last state. Quick does provide forward secrecy. This is with a deterministic key update. So essentially that you're doing some sort of KDF type forward. This doesn't give you post-compromise security. It just gives you forward secrecy. We will get more to that later. And of course, it's used very regularly terrestrially. Excellent. What about space? Well, remember we have these handshakes. It is one round trip. So you're going to go through some sort of client hello, and you need to have the feedback go back and forth. What if you're going around a planet, for example, or moon? We are talking about a variety of cases here at TIPTOP. We voted in that we will talk beyond moon and that we're designing for that. So if you enter a disconnection or disruption phase, that's going to affect your handshake. And again, if you're following the quick specification, as is defined, you're not supposed to send data until you have completed that handshake. Okay. So we have some issues with disruption as one example. Of course, you also have long distances and delays with those. We have the times from minutes even to hours of delay. And what happens if you have to do a round trip? That's a long time to wait before you can start sending data. You also have potentially in space, and certainly what's used in some constructs, where you have unidirectional communication. So it's not just that there's a delay, but you actually have a designated time slot for sending data. And for that, you might actually be waiting a lot longer for a response. So this round trip begins to have an effect, needless to say. And of course, that's pretty realistic in what everyone else is looking at with different space scenarios, LunaNet being just one example. There's a public international effort at combining all these links. So just keeping this sort of picture in mind. And no surprise, but security is actually designed and tailored for a use setting. Going back originally, again, Quick is using the TLS handshake. That was designed, TLS was designed for the internet. Lots of connections, pretty steady connections. Round trips, not really an issue. Of course, we always like to optimize, but it's nothing near when you're talking about waiting minutes to hours for a response. So what do we do about this? So Wesley pointed out in the presentation, his presentation earlier, two factors that are in the current approach. One is to use very, very long-lived sessions, and basically to tweak it so that when you have a disconnection, you aren't going through a zero round trip, but rather you resume the state of where you left off. Early on, so kind of question becomes, how long is long-lived? I'll let the rest of the team talk to what their tests actually were looking at when looking at long-lived, but certainly in the early on conversations prior to the chartering of the working group, what was proposed is to do a single handshake terrestrially before launch, and then keep a single session from then on. I will emphasize here, first of all, if you're doing a single quick session that's living as long as that satellite's out there or whatever device is out there, that's not quick anymore. That's static key encryption. You can't claim quick security if you're not using quick as intended. Also, if you're doing resumption and you're not doing zero round trip resumption according to that protocol, you're not using quick. So at some point when we start tweaking the security of the protocols, it doesn't fit the specification anymore. When TLS says you've got 7 days before you need to rotate keys, and if we're not rotating within those 7 days for quick, we're not using quick. So if we're chartered to use quick, we need to actually use something according to the specification or go back one way or another to that working group and have changes made to adapt for our setting. Okay, problems actually grow. Believe me, we'll get past the problems in a minute. I got the problem part of this presentation. So some of the challenges here with quick. Really it comes down to that one round trip. That's a bit challenging. It's not space, you're dealing with asynchronicity. It'd be really nice to be able to support that. Unfortunately, it doesn't. It does need interactive contribution at each key refresh. So when you're talking about a handshake, that is each side is a contributing freshness. So you don't have, again, any sort of asynchronicity, directional sending. You can't just recover keys in place because you do need both sides to contribute. If we try to hack this into the space setting, it obviously does incentivize some poor security practices, such as very long-lived sessions. We shouldn't be encrypting with a single key for that long. Got the low latency issue. We got performance under the connection loss, namely because you have to do the handshake again if you're doing quick properly according to the spec. And one thing that I will emphasize here also is, what are we going to do about post-quantum? So we all know post-quantum is now kind of the future of protocols. The work is being done in TLS on this and basically every other protocol, security protocol working group here at IETF. Everything needs to be able to support post-quantum. Those key sizes and everything involved with them are very heavy weight on bandwidth. That's going to have an effect under attenuation. That's going to have an effect with your round trip time when you're actually sending data and your recovery. So it'd be very irresponsible, of course, for us to be putting out a protocol if we don't already know in terms of testing and planning that it's going to support the correct post-quantum modes of that underlying protocol. And then there's a few other considerations here, such as post-compromise security, if you're talking like round-trip resumption, zero round-trip resumption, and key update scales poorly, or, that shouldn't be an and, it'll be an or, scales poorly or does not refresh randomness. So in other words, if you're talking about those handshakes, again, it's going to take some time. So a lot of downsides here. And that might naturally be saying, well, are you saying not to use Quick? And the answer is no. Quick is an awesome protocol. It comes with all sorts of features. And of course, we are chartered to work on that. And we realized going into that chartering that there are these issues. So this isn't something that's some sort of surprise. We already expected this. And it is, again, giving lots of fantastic functionalities. So what do we do? Well, remember, all these issues are coming in based on how that key establishment is happening quick, namely that the TLS protocol is slotted in, and that round trip is where we're really incurring this issue, and the key recovery. So it's really that key management side. But Quick is also, once again, very nice in this. TLS handshake was slotted in. You could slot in other handshakes. There have been proposals for Quick using noise handshake. There are proposals right now using, I believe it's called QMUX, looking at Quick more modularly. So there are various people looking at using the Quick protocol. in a fairly modular way where we can actually exchange things out. So then that begs the question, can we keep going with our working quick, but do something a little bit different where we actually keep to the quick spec, but maybe use some other option slotted in instead of the current TLS handshake? And that, I'll hand it over to Raphael.
Thank you, Britta, for explaining in detail what the problem space is. And now we can hopefully move a little more towards what a solution could look like. So I want to take just a minute to zoom out a little bit and talk about encryption protocols more generally before we talk about continuous key agreements more specifically. So to put that in a historic context, encryption protocols have always been about confidentiality, like literally encrypting stuff. To some degree, they've also been about authenticity, at least in one direction, sometimes in both. When you have mutual authentication, broadly speaking, there are like two groups of encryption protocol. One is more for point-to-point transport encryption, and one is end-to-end encryption between actually ends and not just hops in a network. And the two are fairly similar. There are some slight differences. But yeah, by and large, there is a lot of common aspects to them. So as I said, the consensus was early on that we need confidentiality. And later on, we discovered that it might be a problem that, whenever we build up these secure connections, tear them down, and then have a compromise, we can actually decrypt stuff that was sent and encrypted in the past. So that led to the realization that we need something called forward secrecy. It took a long time for that actually to be established in protocols. I think we all remember times when SSL did not have PFS, as it was called at the time. It took a long time to get there. There are some end-to-end encrypted protocols that still don't have that. But by and large, beyond the community of, say, cryptographers, there is consensus that having forward secrecy is a good thing. So that has become the norm for new protocols for sure. And end-to-end encrypted protocols went a little further than that, actually, in terms of security guarantees, because as opposed to transport encryption, they have the problem that they have very long-standing connections, or sessions, rather. It's not really a connection anymore. So if you think about compromise, you not only should think about the past, but also about the future. So if you have a very long-standing session, and you think a compromise has some likelihood, and the question is, how can you recover from that without having to tear down everything, which is not practical, because maybe you don't know when the compromise actually happened. That happened without your knowledge. So that led to what we now formally call post-compromise security. The name is very telling, which is like the temporal opposite of forward secrecy. So these days, when we have a continuous key agreement, this is pretty much what we mean as a package of security guarantees. And as Britta already mentioned, what is really important these days is to think about post-quantum security, because we don't really have the luxury anymore to design something that doesn't accommodate that. It takes a long time to roll out new protocols. Even if we don't have post-quantum or quantum computers today, we want to be ready for that. The downside, and I'm sure you're all aware, the key sizes are huge compared to traditional cryptography. So this is something we have to keep in mind as well. And in order for that to be successful, we need to be efficient at that. That is a real challenge here. Another thing that is also important, specifically between transport and end-to-end encryption, is that asynchronicity is a desired property to have more flexibility in where protocol is actually rolled out. Gonna get back to that slide in a minute. So the question is, do we need something entirely new for a continuous key agreement? And it turns out that we have something that fulfills these requirements exactly, and that is MLS, Messaging Layer Security. That is a continuous group key agreement. We can forget about the group part for now, because if we have a group of 2, we have the 2 ends we actually need. And so it took 5 years to do that. It's been an RFC since 2023. And there was a lot of scrutiny from academia. And the upside here is that we do have a finished protocol that actually meets the requirements exactly. And as Britta already said, this is something we can just slot in instead of TLS into the quick handshake, or replace the TLS handshake. This doesn't mean we need to change other aspects of quick at all. So in a way, it's a bit of a black box thing. So going back to the efficiency of post-quantum key negotiation. So we don't have to do them as frequently as traditional key rotations. So assuming we want PCS, we have to renegotiate keys over time. And we can actually amortize these quite expensive key renegotiations with the post-quantum primitives over time. So just to give you an idea here, this is a measurement of an MLS group with a size of 2. And the numbers are the sizes in bytes for a traditional commit message, which is the handshake messages in MLS. We have about 500 bytes. With post-quantum, we have almost 3 kilobytes. So that's a lot bigger. But if we don't do that every time we do a traditional update, we can actually split that over time, so that if you just look at the size, then the updates, on average, they're barely bigger than the traditional ones. So that means we actually have a realistic chance to be more efficient, even with post-quantum cryptography. And so being, optimizing things and being more efficient is not just an academic, fantasy. It means in some scenarios, stuff can work where otherwise it wouldn't. With TLS, the reality is we have huge handshakes in the beginning and no standardized and formally verified way to renegotiate keys afterwards.
Raphael, I don't understand the claim you just made. Can you back up?
Sure. Maybe we should finish the presentation first, and then we take all the questions. Is that okay?
Sure. Sure.
Probably a bit more. We're almost at the end anyway. All right. So, what do we have today? Today we have a draft for how to put MLS into quick, which is the first iteration of the problem space. And as a little side note, to see if any of that is actually practical, a while back we did something else. We put the MLS handshake into TLS. Just to see, how that works in practice. And the good news is it's really practical, because we can skip a lot of the analysis, because we're not using MLS in a way for which it wasn't designed, actually. So we can simply use that as a building block and replace the TLS handshake. And in practice, it meant that we have something that was ready, really, really quickly, within weeks, essentially. And it gave us a lot of confidence that this is not, a very risky endeavor. So we have this draft today. And yeah, as a summary slide, to reiterate what we just discussed. So with MLS, we have the advantage that it's asynchronous, it is standardized, it's analyzed, like comparatively well analyzed compared to other protocols or other proposals. And we can actually use that today. Whereas, and Britta already covered that, TLS is lacking for scenarios that occur in space. And yeah, so on the security side, we have post-compromise security, which is the big addition, and we think this is really necessary for long-standing sessions, and we can have realistic post-quantum performance that is actually much more optimized than if we do a full handshake every time, as it's the case with TLS. And yeah, I don't know, Britta, do you want to add some closing remarks?
Sure. Okay, thanks. Yeah, so just to recap on some of those problems that we mentioned earlier, including the delays and how you do key recovery after disconnection. What's different here is that you actually have a protocol that's designed for asynchronicity. It was designed with that goal in mind. So it can handle unidirectional sending. It doesn't need a round trip, for example. It can handle disconnection. So when you reconnect, you can immediately start sending data encrypted, and you don't need to go through a handshake phase. And that's by design and by specification. So we're not breaking anything with the spec to do that. So these sorts of things, and you can also control when you do the key updates, because you might say, well, how do you do key updates if not at the beginning? Why do we have to do it at the beginning? That makes sense if you do an internet type connection. But if you're talking about similar types of devices always connecting and always talking to each other again and again and again, then you already can just reestablish that connection, and you can actually schedule when you want to do key updates. So you can put it on a fixed schedule based on your orbit pattern, etc. So there's a lot of options on that. So even though we're not a security working group here, I think really what it comes down to is a few choices for ways forward. We have using quick as is. Obviously, none of the proposals are doing that at the moment. We're currently tweaking how it works, tweaking the lifespan, tweaking how we do key recovery, and so forth. In which case, it probably should go back to the quick working group for that sort of discussion.
But I think we should start to, if you want to have discussion,
Sure.
we should start to have the question.
Okay.
Let's get to the queue.
Just 1 second. And of course, then the other question would be if this is of interest to the working group, in which case we can also take it, for example, to the quick working group or so forth for discussion. So really, it's a matter of what are the questions and then what you want to do about it. All right. We have Eric in the line and then anyone else.
Yeah, can you scroll back to the slide that had the 17, 19 kilobytes, whatever it was? Not that one.
Yeah, try and get the clicker to work here.
Yeah, great. I don't understand what TLS scenario you're comparing here.
Right. So this is coming from various literature tests, usually looking also at the authenticity and certificates, so it's adding up. With post-quantum MLS, post-quantum authenticity is already an option here in these sort of amortizations. So
I don't understand that answer. I don't understand that answer. Like you can just add up the numbers. So we don't need a literature search. You can just add up the numbers. So like tell me what the scenario is.
So TLS working group is still working on the authenticity portion with certificates and for post-quantum.
Yes, in the sense, yeah, I agree with that, but it's just going to be a matter of like, at the end of the day, it's going to be a matter of crossing out ECC and writing in MLDSA.
Right. So that's going to add a lot of extra overhead, unsurprisingly, if you add in the certificates and how many certificates and signatures are in there. These numbers are taken from the literature.
No, but again, the literature doesn't answer my question. Like the bottom line is that all the data is in the key hierarchy. All the data is in the PKI, in the cert chains. And so like, I don't understand why. I don't understand how you get to a situation where when you have the same cert chain, you have dramatically less data in MLS than in TLS.
Okay.
So walk me through that.
I don't think we're here to debate all the TLS options for authenticity.
I'm merely asking you to defend the claim here as opposed to saying it's in the literature.
Well, that's what's in the literature.
No, I understand, but like, okay, like this is actually pretty well understood. You don't need to do like a measurement. So like walk me through it.
No, we're not going to debate TLS here. This is not the working group for that. The literature.
I'm sorry. This
scenario.
Wait a second. Again, like, I don't really want to like hammer on this too hard, but like, this is a straightforward claim. Like, if you're going to make it, you should be able to explain to me what's going on here.
All right. Do you believe, Eric, that post-quantum and TLS can get down to 3 kilobytes?
I don't understand. How does post-quantum, what is the mechanical difference that is making the MLS post-quantum lower than the TLS post-quantum?
Well, remember this asynchronicity, so you really need just one signature on updates. Versus
Okay, now
TLS
I really, now, again, I understand what scenario you're talking about here.
Yes.
You're talking about a TLS full handshake with a full cert chain versus an MLS. Yes, but that's not how you when you update with TLS, you do resumption. And you don't do resignature at all.
That's the point. Yes, exactly. The whole point.
Okay.
So if you're doing MLS, you're only signing the key updates. There is a signature. So in MLS, you're only signing key updates. But the whole point of a continuous key agreement is that you don't have to redo that whole handshake phase again. So the reason why there's such a difference here is that you're essentially skipping going through that full initiation process. Why do we have to reinitialize which entities are talking when that's already known?
But again, that's not how you do TLS resumption. When you do TLS resumption, you skip the entire signature phase.
And in that type, you actually do need 2 KIMs in each direction, and you still have the delay of the round trip. And that's not being currently proposed in any of the current TIPTOP.
No, I'm talking about TLS resumption, not about the thing you're talking about here.
What was that?
I'm talking about TLS resumption, which is not the thing you're talking about here at all.
I mean, we can add in TLS resumption. It's not going to do away with a full round trip.
No, I agree with that. I'm only talking at the byte counting. Okay, well, I think it'd be helpful. I think it'd be helpful if you actually draw out the ladder diagrams for the things you're comparing here, rather than just making a numerical claim.
So I mean,
No, I'm asking you two.
So Ekar and Rita, I think I get to the point like what we were discussing here,
yeah.
But I don't think like this room has the expertise to actually say anything about that one. So that's why in the beginning I said like this working group, if we ever discuss this kind of topic, it's about the requirements on that one. And on that regard, I would say like, okay, let's not discuss like what is there and how it helps the solution space, but let's talk about the problem space. That's like, okay, what do we need in our space to do that, and see like, is MLS quick or like TLS quick helps to solve that one. I think that's like a secondary problem things for me. So I also went to the queue just to relay what Matt wants to discuss. So he would like to have a elaboration on the requirements for the key updates and how that is a problem in Quick plus TLS.
Can you repeat the question?
Elaboration on the requirements for the key updates and how that is a problem in Quick plus TLS.
Right, so with TLS, you've got basically the 3 options. You have the original handshake, which you need to establish. You have 0 round trip, you have a resumption. 0 round trip using a PSK, and still you have to signal in place. So all of this comes down to each of those options requires synchronicity. So it's assuming that there's a synchronous connection between the entities. The current proposals for Quick in space that are saying that this is an efficient and possible way of doing Quick or using the protocol in space do not use any of those methods. We are breaking the Quick specification to say that it fits into this construct. Okay, so when it comes down to is it efficient or is it feasible in that construct, we're not following that specification, which begs the question of should we go back and take what we're currently proposing to the security working groups and say, is it viable? Especially given the long lifetimes that we're looking at. Because when we say Quick is efficient in space, and as you saw already in Wesley's presentation earlier, he said, we needed to make extra long lifetimes to make this efficient in that setting, to make it viable. And that's not according to the spec. So what's really happening is the question is should we go with that version, which is already not to spec, or should we look at something that could be efficient in this setting with another option? So we kind of have choices before us. Either way, it's not going to be debated in this working group. But what does this working group want to do among those options?
Okay, Sean.
Hey, I'll be quick. Hey, again, I'm living near an astronaut. I don't know anything about space. TLS is cool. I think MLS is cool too. I actually chair both working groups. I spent a lot of time flying around the world with Ecker doing TLS 1.3. These are both tools that are in our security toolbox now. MLS did not exist when we did Quick. I don't know what we would have done then, but we probably would have stuck with TLS because Quick was primarily driven by the web. We reach for TLS a lot because it's in our toolbox. And again, it's used on the web and it's very comfortable for people to use. Might TLS work with the additional mechanisms to provide post-compromise security? Probably, it might be fine, right? But the question is, do we want fine? And I just want to reiterate what Martin Duke said in the chat was we should really be looking at the requirements. So we can look at the requirements and figure out what works, and we can agree to those requirements and make sure we get the right people in the room to make those requirements, then we can make a decision. So that's it. Thanks.
Yeah, I think that's a very good comment, and that's kind of echoing like what my thinking on that one. Like, okay, we need to really work on the requirements part of it. We have a use case and requirement document. I would like you all to contribute to that discussion so that we get the requirement right, and then we kind of figure it out like what is the best option for us. Going back to what a response to the Martin, my assumption, like in the charter also, like quick is a starting point, but doesn't mean like if the requirement analysis say like, hey, we don't need a quick or like quick like thing, we need, so that could be a thing as well. But I think our suggestion is like, let's work with this use case and requirement document, and let's get the requirements right. Agree in this working group, we work on requirement, agree on that one, and maybe in TLS working group, we fix, or quick working group fix like whether MLS or TLS or other options are best.
So I like the idea of the requirements document a lot. And I think that a lot will come out of that. I do have a question though. So we obviously have a lot of motivation in the room and trying to move quickly. We also have this other draft that is kind of pending calling for adoption on using quick with these current modifications, not the ratcheted key exchange, but with other modifications. And the question is, are we holding up that draft? Because we do have this sort of time factor, or do we want to like call for a vote and see should these be explored equally? What of those do you think you want to do?
I mean, I would do. I would basically focus on the use case and requirement document right now and the architecture of it, and then the solution one. But
I just wanted to interject because we really don't have time. I was going to suggest something is that we have more discussion on the alias. And if need be, we can have an interim meeting to have a working meeting on some aspects to bring people together. I don't think we can find an answer in this room today, nor on the alias. So let's try and work on how we can actually work on and organize ourselves for the next meeting.
Okay, great. Okay, with that, I think I'd like to thank everybody for your questions. And still you haven't registered yourself, use the QR code. I'm just a bit sad, like we lost 2. It was 100 attendee. Thank you. See you in Montreal.
Thanks, everyone. Bye-bye.
I mean, the thing. I don't know, like, if you can answer that right now. I mean, I would like to say this is from a management point of view. And that should not block us to discuss other things. But when it comes to adoption, I think I'd like to see after your presentation and you coming in this workshop, and thanks for doing that. I think we might actually need to have more discussion before we take anything on board as a solution space. So that would be the case. I mean, obviously, the thing is like what is not in the chat. If you want to say like, hey, the requirement MLS is actually right choice, we don't have the opportunity to change it. So I make sure you get charging this for